Hi everyone. Am I audible? And the audio is clear? Any disturbance in the audio? Okay then, let's start. And today the main topic that we will study is first order logic, also called predicate logic. Yesterday we have already seen the topic propositional logic, but let me just quickly give you the recap of propositional logic, and then we will move on to the topics of predicate logic. If anyone has any doubt anytime, then you can ask in the comment box. I will see and I will answer your doubt. Okay, so let's start. So propositional logic, we were studying this propositional logic yesterday. Let's see a quick recap. We know what is a proposition. Proposition is a statement which is hello. Just wait a second, let me increase the volume. Hello. Let me increase some volume. Just give me 2 minutes. Hello. Hello. Is the volume okay now? फैन फैन बंद करूँ क्या? हेलो 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 yes now is it okay? Hello sir. OBS. Okay, so shall I resume? Hello. Hello. Yes sir. Yes sir. गेन गेन कम कर रहा था मैं तो. हेलो. हाँ गेन कम ही है. हेलो सर. यस सर. हेलो. नाउ इज इट ओके? Okay. Now shall I resume? Okay everyone, let's resume now. Sorry, I was just checking whether the audio is perfect or not. Okay. If anyone face any issue, then you can just let me know in the comment box. I'll be looking at the comment box after every 5 minutes. And now let me start. Okay, so yesterday we were studying propositional logic, and we had seen what is a proposition, what is a propositional variable. We know that propositional variable is a variable basically that represents a proposition, and a proposition is a statement which is true or false. So a propositional variable, any propositional variable, is basically either true or it is false. Okay, so any propositional variable, p, q, all these things, they can be either assigned true or we can assign them false. We can either assign them true or we can assign them false. These are the two values. Basically any propositional variable p, this can only take one of these two values. One of these two values it can take, either true or false. We had seen logical connectives also. Some logical connectives we saw, like negation, conjunction, disjunction, implication, biconditional, and of course these are just true comma false. So we denote true by t and we denoted false by f, but this is just a convention. Sometimes they will give you in the question, if they are using different convention, then they will give you that okay, they are using t for true and they are using this this symbol for false. Anyway, this is just a convention. We are using this convention. For true we are using t, and for false we are using false, f. So this is the recap, and basically yesterday's class was completely revolving around these connectives. So we have already seen all these things. Now let's move on. And so the one topic that was remaining yesterday was operator precedence. Let's see operator precedence now. Okay, I'm just looking at the comment box. If anyone has any doubt anytime, you can ask in the comment box. Okay. Yes. So now let's see what is operator precedence. In mathematics, if you write this kind of statement, 3 plus 4, let's assume this kind of statement, if you write 5 multiplied by 3 plus 4, in mathematics, whenever you write this kind of statement, then what do you mean? What do you mean? Do you mean like this, first you do the multiplication, then you do the plus, or first you do this addition, then you do the multiplication? Which of these things you mean? This is first and this is second. Let me know. Whenever in mathematics, in general mathematics, whenever you do this, whenever you write this kind of equation, then what do you mean? Do you mean this or do you mean this? The first or second? Let me know quickly. The first or second? Yes. So everyone is saying first. Yes. So you mean first. Basically, in mathematics we have this convention. This is a convention. Basically, everyone has adopted this convention that first we do multiplication, then we do the addition. So basically, we say that this multiplication has higher precedence, higher priority than addition. This multiplication has a higher precedence than addition. So we do like this. Similarly, in our propositional logic also, the operators have different precedence. For example, if I write this kind of statement, negation P and Q implies R. If I write this kind of statement in propositional logic, then what do I mean? Like which operator has high precedence, which operator has low precedence? Here we have three operators: the negation, there is conjunction, and there is implication. These three operators we have here. So which of them has high precedence, which of them has low precedence? So that is known as precedence order. That is known as precedence order. What is precedence order? So the highest precedence is negation. This negation has highest precedence. And then we have conjunction. So this conjunction has, so this is the highest precedence, means this is first number. So it has the highest priority. This negation has highest priority. The second we have conjunction. The third we have disjunction. The fourth we have implication. The fifth we have by implication. So this is the precedence order. So if we look at this precedence order, then what will be the interpretation of this formula? So we know that the negation has higher precedence. So first you will do the negation. Then we know that conjunction has higher precedence than implication. So now you do the conjunction. And then you do the implication. So this is known as precedence order. Okay. So this is the precedence order. This negation has highest precedence. And then we have conjunction, then disjunction, then implication, and then by implication. So this is the precedence order, and the precedence is basically decreasing whenever we go from top to bottom. Then basically from first to fifth when we go, then the precedence is decreasing. Okay. So this is how we interpret our formulas. Okay. Let's take one more example and then let's see. So if we have this kind of statement, let's assume we have this kind of statement. Let's assume we have this kind of statement. Then what will be the interpretation of this statement? You can try on your own. There is no need to write in the comment box, but you can try on your own. What will be the execution? Like what will execute first, what will execute second, what will execute third, these kind of things. Like in mathematics, whenever we write this kind of equation, whenever we write this kind of equation, then what we mean? We mean that first multiplication will happen. So the first thing that will happen is multiplication, and then the next thing that will happen, actually this subtraction and plus, they have both have equal priority. Whenever two things have equal priority, for example 2 plus 3 plus 4, you see this plus and this plus, they have equal priority. Whenever two things have equal priority, then we see something called associativity. So associativity says that whenever two things have equal priority, then do it from left to right or do it from right to left. If we do it from left to right, then what will happen? Then it will happen. If we do from right to left, then what will happen? Then it will happen. So you see, this means left to left associative. This means left associative. Remember, this associativity concept comes in picture when two things have equal priority. When two things have equal priority, then how do you execute them? So this thing is known as left associative. Means first you do the left side, then you do the right side. This thing is known as right associativity. Right associativity. Okay, this thing is known as right associativity. So here if you see, in mathematics we have left associativity. This subtraction and addition, they have both same priority. So the associativity comes in picture. So in mathematics we use left associativity. So what happens? Now basically you will do this minus first and then you will do the addition. So two concepts are here. The first concept is precedence. Precedence means priority. Who has more priority? And the next concept is associativity. Associativity, whether left associativity or right associativity. This precedence says which to execute first. For example, 3 into 4 minus 5, then the precedence of multiplication is more. So you do multiplication first, then you do the subtraction. But what will happen if you have two operators side by side? Two operators side by side, they have equal precedence. This multiplication has equal precedence to this multiplication. So what you do? Then the associativity comes in picture. Then you apply this associativity. So in mathematics, the multiplication is left associative. So what you do? First you do this, then you do this. So first you execute this left multiplication, then you execute the right multiplication. So these are the two concepts we have in every field of mathematics. In every field, almost every field, we have these two concepts, precedence and associativity. Similarly, in our field, in our propositional logic field, first order logic field, mathematical logic field, also we have this concept called precedence and associativity. So how will we execute this statement? We know that negation has highest priority. So you do the negation first. First you do negation. Now we know, see, okay, we have done the negation. Now we have two things. One is this conjunction and another is this implication. What we should do first? So we should do conjunction first, because conjunction has higher precedence, higher priority than implication. So next thing we do is this conjunction. Now we have two things. You see, we have implication and we have this conjunction. So what we should do? Similarly, we have this disjunction. Three things we have: implication, conjunction, disjunction. What we should do first? So first we should do conjunction, because conjunction has more precedence. So you do conjunction. Then the remaining thing is implication and disjunction. So we know that disjunction has more priority. So you do disjunction. And then at the last you do the implication. So this will be the execution order. This is how you will execute these statements. Okay. So anyone has any doubt in this? Precedence, associativity. So this is written here. You can see in this slide, this is written here. This is the operator precedence. The negation has highest precedence, and whenever we go from top to bottom, then basically the precedence is decreasing. And remember, whether in our propositional logic, all the operators are right associative. So if I write like this, let's assume I write like this, P and Q and R, then what will be, then what we should do? Whether we should do the left conjunction first, whether we should do like this, or whether we should do like this. What we should do, this or this. So actually most of the authors, most of the professors, they prefer right associativity, means do the right operator first. So this is what we will do. But remember, this is not a universal thing. If you are studying from some author, let's assume author 1, then this author 1 may use left associativity and author 2 may use right associativity. So author 1 will do like this, author 1 will do like this, and author 2 will do like this. Okay. So but most of the authors, they use right associativity, most of the authors. So in NET exam they will mention it, don't worry about it, they will mention whether something is right associative or left associative. But if nothing is mentioned, let's assume nothing is mentioned, then you use right associativity, because most of the authors use right associativity. Okay. And so this is about operator precedence. If anyone has any doubt, you can ask, or we can solve one more question, we can solve maybe. So negation of P and negation of Q, implication R. What will be the execution? What will be the execution order? We can also write like this, maybe R and Q, R disjunction Q. So what will be the execution order? We know that negation has the highest priority, so you do the negation first. And negation has the highest priority, so you do the negation. So you do this negation, this negation. Then conjunction has higher priority than implication, so you do the conjunction first. Now implication and disjunction are remaining, so disjunction has higher priority, so you do disjunction first, and then at the last you do this implication. So this is about operator precedence. Okay, let me see if anyone has any doubt. You can ask in the comment box. Okay, so if let's do one thing, because there are many messages, so I do not know which is doubt and which is reply, because some students are asking doubt and some students are replying. So do me a favor, if you are asking a doubt and you want me to solve it, then you write doubt, so you start with doubt and then you write your doubt, so that I directly know which is doubt and which is reply. So you can see many messages are there in the comment box, so it's hard to go through all the messages. So whenever I will see this word, this doubt word, then I will quickly be able to see your doubt. Okay, so do this whenever you want me to answer something, whenever you have some doubt and you want me to answer. If you are replying, then you do not write it. Okay, so you start your doubt with doubt and then you write your doubt. Okay, now let's see the next topic, that is translating into propositional logic. So now what we will do, we will have some statements, some English statements, and we will translate them to our propositional logic formula. For example, let's assume that P is a proposition. P is a proposition that today is Friday. Today is Friday, let's assume. Okay, and Q is a proposition, it is raining. It is raining, let's assume. So this P is a proposition, today is Friday. This Q is a proposition, it is raining. Now if I want to write this, let's assume I am writing a English statement, today is Friday and it is raining, and it is raining. So for this statement, remember, for this statement, what will be the propositional logic formula? So this is what we want to see now. So you see, this is the proposition, today is Friday. What is today's Friday? Today's Friday means P, because P is representing this proposition, today is Friday. And this Q is a propositional variable which is representing it is raining. So this it is raining, this is represented by Q. Now this and is represented by conjunction. I already told you in yesterday's class, this and is represented by conjunction. Basically this symbol means and. So this means P and Q. So this English statement, we have converted this English statement into propositional logic formula. So this is the propositional logic formula for this English statement. Now let me know, just quickly let me know, if I replace this and with or, then what will be the propositional logic formula? If I replace this and with or, so basically my statement is today is Friday or it is raining. So what will be the propositional logic formula for this? Let me know quickly. What about brackets precedence? So someone is asking what about the bracket precedence? Bracket always has the highest precedence. Even in our mathematics also bracket has the highest precedence. Here also bracket has highest precedence. Let me solve this question first, then I will tell you what about bracket precedence. So let's solve this question. This will be P or Q, because today is Friday, that is represented by P. It is raining, this is represented by Q, and this or is represented by disjunction. This is the symbol for or. Okay, let me quickly tell you about the bracket precedence. So just like in mathematics we have this kind of, for example, let's assume in mathematics we have this statement. Let's assume this statement we have in mathematics. Then you already know that this bracket has higher precedence. So what we do, basically first we do this, then we do this. So the result will be 7 multiplied by 4, that will be 28. Okay, because bracket has highest precedence. Similarly here also, if we have this statement, let's assume that we have this statement. Now if we have this statement, then first we will do the implication. Why? Because bracket has the highest precedence. So first we will do the implication, then we will do the conjunction. Okay, but remember, if we have this without bracket, if we have this, then what we do, then the precedence order says that first you do the conjunction. So first you do the conjunction, then you do the implication. This is the precedence order. So basically this thing means this. Okay, and now you can see this bracket has the highest precedence, so you do the bracket first. Okay, if anyone has any doubt, then you can ask, and let me see if there is any other doubt or not. So Prerna, is your doubt clear? What about bracket precedence? Bracket always has highest precedence in any field of mathematics. It does not matter whether you are studying mathematical logic, or whether you are studying mathematics, or whether you are in 9th class, 12th class, college, whatever. Bracket always has highest precedence. So okay, now let's move on. So we were seeing how to translate an English statement into propositional logic formula. Let's have one last example. Let's have this example. This English statement I am giving you. If today is Friday, then it is raining, Let me know what will be the propositional logic formula for this statement. This statement we have, if today is Friday, then it is raining. What will be the propositional logic formula for this statement? Right. So we have seen yesterday one thing, that this P implies Q. How do we read it? We read it like this. If P, then Q. This is how we read it. So remember, this is the first order logic formula. Sorry, this is the propositional logic formula. Okay, this is the propositional logic formula, and this is the English statement. So this P implies Q. How do we read it in English? We read it like this. If P, then Q. In Hindi, if you want to read it, then how will you read it? Yadi P tab Q, I think. Yadi P tab Q. So anyway, so you can see this is how you can read any propositional logic formula in your natural language. This English language, Hindi language, Tamil language, Malayalam language, in any language you can read this formula, this P implies Q, this formula you can read in your natural language like this: if P then Q. So this English statement is also of the form if P then Q, if then, and now this is our P, because you can see today's Friday is represented by P. It is raining, it is represented by Q. So we have if P then Q, and if P then Q, how do we write it? We write it like this: P implies Q. Okay, so let's see few more complicated examples. Let's see this example. So this is a complicated statement. Finally, basically you need to convert this statement. Let's right now, don't look at this solution, you make your own solution. Okay, so you see, some propositions have been given to you. The proposition variable A, this is the propositional variable. Remember, this is just a propositional variable. This is representing this proposition. So this is the proposition represented by this propositional variable A. What is this proposition? There is a velociraptor outside my apartment. Maybe you are in the Jurassic World, whatever. If you are a fan of Jurassic World, then you will like this example. And the proposition variable B, this is representing this proposition: velociraptors can open windows. If you have seen the Jurassic World movie, then I think in the third movie they have this capability that they can open window, they can camouflage. Anyway, so this is the third propositional variable. This C, this is a propositional variable, and this is representing this proposition: I am in my apartment right now. And the fourth propositional variable D, it is representing this proposition: my apartment has windows. And E, this is the last proposition variable that we have, and this E is representing this proposition: I am going to be eaten by a velociraptor. So these 5 propositions you have, these 5 propositional variable you have, and now you need to, okay, again don't look at this solution. So now you need to convert this English statement. This is the English statement I have given you, and you need to convert this English statement into propositional logic formula. What is this English statement? I won't be eaten by a velociraptor if there isn't a velociraptor outside my apartment. Okay, this is the statement you have, and you need to convert this statement, this English statement, into propositional logic formula. Try this question. So this is just, we have just taken some complicated statements, we have taken, nothing more than that. So you try this question. Also, you might get different propositional logic formula, because I told you that sometimes different propositional logic formula are equivalent. Yesterday we saw this. If you remember yesterday we saw this, that P implies Q. This thing, this formula, remember this formula F1, let's call it formula F1, then this is equivalent to P dash plus Q, let's call it formula F2. So this formula F1 is equivalent to formula F2. So if you answer, let's assume your answer is F1 and your friend's answer is F2, then remember both your answers are correct. Okay, so sometimes you can get different propositional logic formula, but they can be equivalent. If they are equivalent, then that is correct answer. So let me answer this question. If you see this answer, if you see this question, then what it is? It is saying, I won't be eaten by a velociraptor. First let's cover it. So what is this? I won't be eaten by a velociraptor. If you see this E, then what is E saying? E is saying I am going to be eaten by a velociraptor, but this statement is saying I won't be eaten by a velociraptor. So basically this much statement, we can write it like this: negation of E. Because this statement, if you see this statement, this much statement, if you read, then this is basically negation of E. Okay, then we have if. Then we have, there isn't a velociraptor outside my apartment. If you see this statement A, then this statement A is saying there is a velociraptor outside my apartment, but this statement is saying there isn't a velociraptor outside my apartment. So basically this statement, this much statement, from here to here, this much statement can be represented by negation of A, right? Because this is a negation of A. The only thing that is remaining is if. The only thing that is remaining is if. So what should we do? Now someone might be thinking maybe we should do this, maybe because maybe we should do this. Some might be thinking maybe we should do this. Which of them is correct? Like what side we should imply? Whether this is correct, first is correct, or second is correct? Let me know. What do you think? First is correct or second is correct? I have given two formula. First is correct or second is correct? Let me know. Anyone want to answer? Which of these is correct? First or second? Yes. So actually second is correct. Because if you remember, I told you, whenever we have this kind of statement, if something, if P then Q. Remember, if this kind of statement, if P then Q. So if you see, this P has this if P. So this is the condition, if P. So this if P. So we translate it like this. Remember, we translate it like this. We do not translate it like this. So this is not a correct translation. This is the correct translation, because whenever we have if P, then this P will go to the LHS of implication. Remember, this is the implication. This P will go to the LHS of the implication. Okay. So if P then Q, we write it like this. P implies Q. Okay. So this P will go to the LHS of implication. Similarly, here if you see, the if is with negation A. This if you see this if, then this is with negation of A. So this negation A will go to the left side of the implication. So this is the implication. The left side of the implication will be negation A, and the right side will be the remaining thing, that is negation E. So this is the correct. Remember, this is the correct. Okay. So let's note this point. You can note this point. Whenever we have this kind of statement, P if Q, remember this if is applied to Q. So how will we translate it? This Q will go to the left side of the implication. So we will write it like this. Q implies P. And remember, this thing is same as if I write like this. Both are same, because both are same. This means Q implies P. This also means Q implies P. So remember, both these things are same. Q implies P, Q implies P. Okay. So these both are same. So whenever we have this kind of statement, P if Q, then this if is with Q. This if is with Q. So this Q will go to the left hand side of implication. So you will take Q implies P. You can very easily remember it by this fact, that whenever we have this kind of statement, if P then Q, then how do we write it? Because this if is applied to P, so we write it like this. P implies Q. Okay, remember, so this does not translate like this. This is the correct translation. Okay, how do or maybe if you want to remember it, then you can remember like this. Whenever you have a conditional statement, whenever you have this kind of a statement, if then this kind of a statement, then you write it like this. P if Q. Okay, so remember, this if must come in between. So this if must come in between. So P if Q, this is Q. Okay, this is Q. P if Q. So basically you have a P, you have a Q, and in the middle you have if. Whenever you have this kind of setting, then remember that this if goes backward. This if goes backward. Okay, so this is the correct. Remember, whenever this if is in the middle, then this if goes backward. This is the trick. So remember, your correct translation will be this. Q implies P. So this is same as this. Q implies P. This is not correct, because it is saying P implies Q. It is saying Q implies P. It is saying Q implies P. Okay. So anyway, if anyone has any doubt, then you can ask. Else, let me tell you few more things. In English, whenever we write and, or we write but, remember, in English, whenever we write and or we write but, these kind of words, these kind of English words will mean conjunction in our these words will mean conjunction in our propositional logic. Remember, these are the English words. So I am just telling you, if you have English words, then how will you translate them? For example, let's assume you have this statement, P and Q. Then how will you translate it? You will translate like this, P conjunction Q. Similarly, this but also means and. So remember, this but is same as and. This but, we will think of this but as and. So whenever you have this but, then you just convert this, you just replace this but with and. Okay. Similarly, whenever we have this kind of statement, if P then Q, this you already know. This will be P implies Q. This you already know. Also, sometimes what we do, we sometimes remove this then. What will we get? We will get this, if P comma Q. If P comma Q. So this then can be replaced by comma also. So this is also P implies Q. Sometimes what we do, this if is same as when, or this when is same as whenever. Okay. So if I write like this, let's assume I write when P then Q, then how will we translate it? We will translate it like this, P implies Q. Why? Because this when is similar to if. This if, when, whenever, they have the same meaning. So this you need to, just because these are English words, so these are equivalent English words, we will always take them as same. If, when, whenever, these are same. Okay. Now let's see. So if you have this statement, P but Q, then this will be translated as P and Q, because this but means and. Okay. So let's see this, and don't look at the answer, and translate this English statement into propositional logic formula. The same statement you have, the same 5 statement that we took earlier, those same 5 statement we have taken here. You need to convert this English statement into propositional logic formula. Try this question. Try this question. Don't worry, today what I will do, because today this mathematical logic will be over, तो मैं क्या करूँगा कि ये जो स्लाइड हैं ये मैं आपके साथ शेयर कर दूँगा. Devika is saying please speak Hindi also in between. Okay, Devika. Okay, so before I see this example, let me tell you something. If you see this statement, just focus on this statement, P if Q. You already know, whenever you have this kind of statement, then you write it like this, P imply this, because this if goes backward, you already know. This if goes backward, you already know this thing. Remember, this trick will work when you have this if in the middle. So you have a statement, then you have if, then you have Q. So whenever you have this kind of setting, then this trick will work. What is the trick? Trick is this if goes backward. This is the trick. So this trick will work only in this case. Remember, this trick will not work in this case. Okay, remember, this trick will not work in this case, because this if is not in the middle. So don't apply this trick here. If you apply, because maybe you can apply like this. You will say, because Deepak sir said that if goes backward, so I will write like this, if goes backward. No. This is a trick. Remember, this is a trick, and this will work when you have a statement in the middle. You have if, then you have Q, then it will work. For example, if I want to convert this into this setting, this is our setting, this is our correct setting, this is the setting we want. So if you have this statement, then you can convert this statement into this setting. How will you convert? you will convert like this, because you can write it like this, q if p, because this if is with p, you see this if is with p, so you can write like this, q if p. So you can see this if is with p. Now you can, what you can do, now you can apply this trick. The trick says that if goes backward, so now you apply this trick, if goes backward. Okay, so let's see one more statement. What is the difference between these two? What is the difference between these? The one is this. What is the difference? इन दोनों में क्या अंतर है? एक है हमारे पास में स्टेटमेंट P if Q, एक तो ये स्टेटमेंट है हमारे पास, एक दूसरा स्टेटमेंट है P only if Q. ये दो स्टेटमेंट है हमारे पास. What is the difference between these two statements? Can you feel some difference? Some difference can you feel? Yes, you can feel some difference, because this is saying P if Q means basically it is saying that this P if Q. So if Q is true, then P is true. This is saying like this. So for example, maybe this P is this P might be some statement. For example, I am teaching discrete mathematics. This Q might be a statement, my name is Deepak Punya. So what it will mean, basically it is saying that if my name is Deepak Punya, then I am teaching discrete mathematics. Okay, but what it means, it is saying that P only if Q means I am teaching discrete mathematics only if my name is Deepak Punya. So you can see there is a difference here. Okay, it is saying that I am teaching mathematics only if my name is Deepak Punya. Basically, if my name is not Deepak Punya, then I cannot teach discrete mathematics. Okay, because this only if is a different thing. This only if is some mandatory situation, some necessary situation. It is saying P only if Q. Like your mother is saying, तुम खेलने जा सकते हो only if you do your homework. Only if. So when she says this only if, then basically she is a very strict mother, and she is saying that only if you do your homework, then you can go to play. But if your mother is saying you can go to play if you do your homework, then basically not so much strict condition. Okay, so let's see. Basically, these are two different things. So this P if Q, this thing is different from P only if Q. So remember, this if is different from only if. Okay, so how do we translate when we have this kind of statement? When we have this kind of statement, when we have, then how do we translate? We know how to translate this. P if Q. So this if goes backward. So this is how we translate because this if goes backward. How do we translate this? This only if goes forward. So this only if will go forward. Remember, in this setting, there must be a statement. In the middle, you must have only if, and there must be a statement. So in the middle, you must have only if. Similarly, in this setting also, this if must be in the middle. So if you have this kind of statement, P only if Q, how will you translate it? You will translate it like this, because this only if goes forward. So you will translate it like this. P implies Q, because this only if goes forward. This if goes backward. So this will be P implies Q. And what is this? This is Q implies P. You can write like this, Q implies P. Okay, this is Q implies P. Remember, this is like this. Okay, so this means Q implies P. Okay, so this thing and this thing is same, Q implies P. And this is P implies Q. These are two different things. So just take care of this concept, like only if these are two different things. Now let's solve this question. This question is saying, I am only in my apartment when there is no velociraptor outside. So basically there is a only word here. If you see, there is a only word here. So this English statement, I will rewrite it. I can rewrite like this. I am only in my apartment. Basically, I am. This only I will remove, because if you see this. See this C. In this C there is no only. In this C there is no only word. This only word matters a lot. In this C there is no only word. So first I will write this C. I am in my apartment. Okay, I am in my apartment. Now I can write like this. I am in my apartment only if this. Remember, this if is similar to when. So you can apply like this. Only when this only when, only if, these are same things. I told you if is same as when. So I am in my apartment only if there is no velociraptor outside. There is no velociraptor outside. Anyway, now you know this is a statement. So you see this is a statement. In the middle you have only if, then there is a statement. So this only if will go forward, this only if will go in the forward direction. Before this only if you have I am in my apartment, that is C. After this only if you have this statement, no velociraptor outside my apartment, so that is nothing but negation of A. So this is how you will convert. Any doubt in this? Remember, this only word is not in our statement C. So this only word gives a different condition, because this word if is different from the word only if. Only if is a strict word. Okay. So anyway, so this is how we convert it. Always use our setting. This setting I told you, use this setting. Only if must come in the middle. First you put only if in the middle, you put a statement here, you put a statement here, and now the only if will go forward direction. If anyone has any doubt, then you can ask. Okay, let me see this doubt. Sir, P only if Q and if P then Q both are same. Yes, both are same. Okay, so but remember, this is the setting, this is our trick. This trick of going forward, going backward, this trick will work in this case when this only if they are in the middle. In other cases, for example, in this case our trick will not work. In this case our trick will not work. So what I should do? First I should convert this in our setting. So how can I convert it? Remember, this if is with P. This if is with P, so I can convert like this, because I want to take this if in the middle, because this trick will work only when this if, only if these are in the middle. So now we can use our trick. Our trick says that if goes backward, if goes backward, if goes backward, only if goes forward. Doubt? If only if is in the starting. So if only if in the starting, then how will we do? Let's assume this is only if P then Q. Now again you do the same thing. First convert this into our setting. Our setting says that, remember, this only if is with P. So our setting will do like this: P Q only if P, because in our setting only if will come in the middle. But remember, this only if is applied to P, so this only if will apply to P. So in our now this statement we have converted in this setting. Now you can apply. So what will you get? You will get, because only if goes in forward direction, is equivalent to if whenever is equivalent to P implies Q. So I told you this word, this English word if is equivalent to the English word when. This word is equivalent to this English word whenever. These three English words are equivalent. Okay. So if anyone has any other doubt, then you can ask. If your doubt is clear, remember, if your doubt is clear, then okay. But if your doubt is not clear, then you can repeat your doubt. So I will know that your doubt is not clear. If के बाद के भी variable होगा, that will come before implies. So Devika, did you get this point? Just put if in the middle. Just put if in the middle. Put something here. Put something here. Now the if will go in the backward direction. So finally you will get Q implies P. Q implies P. Okay. So let's move on. So this is how you can translate. So remember this thing. P only when. Remember, this when is same as if. So you can replace this when with if. So you will get P only if Q. And this only if will go in the forward direction. So you will get P implies Q. Let's see the last topic in propositional logic. The propositional logic is over. This is the last topic that is remaining. Logical equivalence. This topic actually we have already seen, but we did not. Many times I have said this formula is equivalent to this formula. This formula is equivalent to this formula. All these things I have said many times. So this is same. If you remember, yesterday I said that this formula, let's call this formula F1. Let's call this formula. So this is the formula P implies Q. Let's call this formula F1. So yesterday I told you that this formula is equivalent to this formula. So let's call this formula F2. So F1 is equivalent to F2. I told you this thing yesterday. So basically this F1 formula is equivalent to F2 formula. So you can replace them whenever, let's assume you have formula F1, then you can replace this formula F1 with formula F2 because they are equivalent. Similarly, whenever you have this formula F2, then you can replace this formula F2 with F1. This is what we mean by equivalent. Basically they are equivalent. Like if I say that let's assume Akshay Kumar is equivalent to okay, anyway, whatever your favorite Akshay Kumar is equivalent. In Hollywood we have Tom Cruise. So if I say that Akshay Kumar is equivalent to Tom Cruise, okay, don't mind me. If you are a fan of Akshay Kumar or Tom Cruise, then don't mind me. But the thing is, if I say that Akshay Kumar is equivalent to Tom Cruise, then what I mean that whenever you have Tom Cruise in any movie, you have Tom Cruise, you can replace him with Akshay Kumar. Akshay Kumar can also do those things. Similarly, in any movie, if you have Akshay Kumar, then you can replace him with Tom Cruise. So these kind of statements we say in our daily life also, that this thing is equivalent to this thing. We say these kind of things. Okay. So like before this IPL, we would say that Chennai Super Kings is equivalent to Mumbai Indian because these are the top teams. So anyway, basically two things are equivalent. Then you can replace one with another. Similarly here, this formula F1 is equivalent to formula F2. So you can replace this formula F1 with formula F2. Also, you can replace this formula F2 with formula F1. Why do we say that they are equivalent? Why do we say? We say they are equivalent. Why? Because their truth table are same. If you construct the truth table of P implies Q, yesterday we have already constructed it. And also if you construct the truth table of P dash plus Q, then you will see that both have the same truth table. Okay. If you construct truth table of F1, this is the F1, this is truth table of F2, then you can see both have the same truth table. So we say that they are equivalent. Why? Because whenever F1 is true, whenever F1 is true, for example, in this case F1 is true, you can see in this case F2 is also true. Similarly, you can see in this case F1 is true, in this case F2 is also true. In this case F1 is true, in this case F2 is also true. Similarly, in this case F1 is false, F2 is also false. So whenever we say that a formula F1 is equivalent to formula F2, a formula F1 we have, a formula F2 we have, and whenever we say that they are equivalent, then basically we mean that whenever this is true, then this is true. Whenever this is false, then this is also false. Okay. So this is what we mean by equivalence. Let's take one more example. Yesterday I told you that this P implies Q. This is not equivalent to Q implies P. Why? Because if you see the truth table of these things, if you see the truth table, you can construct the truth table of these things. You can very easily construct the truth table. We have already constructed it yesterday. So if you construct the truth table, then what you will get this. You can see these are not same. This is 1101, this is 1011. So this truth table is not the same as this truth table. So let's assume this is formula F1. Let's assume this is formula F2. Then the formula F1 truth table is different from truth table of formula F2. So we say that these are not equivalent. Why are we saying that these are not equivalent? Because if you take one situation when P is true, let's assume this situation, when P is true, Q is false. Take this situation. In this situation, this formula F1 will become false. In this situation, the formula F1, this formula F1 will become false, but this formula F2 will become true. You can see, because this formula F2 will become true. Why? Because Q is false, and whenever LHS is false, then automatically the implication becomes true. This we have seen yesterday. Whenever the LHS of the implication is false, then the complete implication becomes true. This we have already seen yesterday. So you can see this in this situation, this formula F1 is false, the formula F2 is true. So we can say that they are not equivalent. Like if you make the movie Hera Fairy, okay, then in this movie you take Akshay Kumar. So Akshay Kumar is a good comedian. But if you take Tom Cruise in this movie, then maybe you won't get that comedy, maybe, I don't know. So but let's assume that when you take Akshay Kumar, then it is a very nice movie. You take Tom Cruise and now it is ruined. Now this movie is ruined. So you can say that they are not equivalent, because in this situation, the Akshay Kumar is true, the Tom Cruise is false. So anyway, this is what we mean basically. Whenever you remember, whenever you are saying that two things are equivalent, then what it means that in every situation they are equivalent. In every situation, whenever this F1 is true, in that situation F2 should also be true. In any situation, if F1 is false, then F2 should also be false. Okay, so this is what we mean. For example, if you have a Rajnikant movie, then in that Rajnikant movie, if you put Akshay Kumar, then it will be a false. We won't enjoy it. Similarly, in a Rajnikant movie, if you put Tom Cruise, then also Tom Cruise is also false. So both are false. So basically, in every situation, both must be same. So this is what we mean by two things being equivalent. Now let's see some formulas which are equivalent. We have seen one thing yesterday, De Morgan formula. The De Morgan formula was like this. If you do this, P and Q negation, we know that this formula, let's call this formula F1. This formula F1 is equivalent to this formula F2. This is De Morgan rule. This is De Morgan rule, if you remember. In De Morgan rule, what we do, this conjunction is replaced by disjunction, and this P is replaced by P dash, Q is replaced by Q dash. This is De Morgan rule. So this formula F1 is equivalent to this formula F2. Why it is so? Because if you construct the truth table, then you will see that both have same truth table. You can see this truth table. So this is basically, this is nothing but conjunction negation. So this is P and Q bar. So if you see the truth table of this, then what you will get, the truth table of this you will get, okay, don't focus here, this is just a truth table of P and Q. So finally you will get this is the truth table of this. For this statement, for this formula F1, this will be the truth table, true, 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 false. Similarly, for this F2 formula, you will get this truth table, this yellow truth table. Just focus on this yellow. So these yellow things are same, true, 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 false, true, 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 false. So that's why we are saying that these two things are equivalent. This F1 is equivalent to F2. Why? Because their truth table is same. It means that whenever F1 is true, then F2 is true. Whenever F1 is false, then F2 is false. Okay, basically they both are always same. They both have same truth value every time. Okay, they both will have false together. They both will have true together. Okay, so they will basically share their truth value in every situation. That's why we are saying that they are equivalent. Okay, you can see more examples if you. So this is the formal definition. We have already seen this definition. So whenever you have two formula, let's assume the one formula is psi and the another formula is, let's assume, some other symbol you can use, maybe I don't know, some phi. Let's assume this is the formula psi, this is the formula phi. If two formula are equivalent, then what it means, their truth table is same. Whenever this is true, then this is true. In any situation, if this is false, then this is also false. Okay, so this is what we mean by logical equivalence. These De Morgan rules, these De Morgan rules we have seen yesterday. So this formula is equivalent to this formula. Similarly, this formula is equivalent to this formula, and these rules, these two rules are called De Morgan rules, De Morgan laws. But remember, this thing is equivalent to this thing is equivalent to this, because basically they have the same truth table. Now the next thing, if I ask you, this is important actually, because I told you yesterday that this implication, P implies Q, this implication operator is very important in discrete mathematics. So now my question is, when will this become false? Let me write it F1. So this is F1, P implies Q, this is F1. Okay, so let's call this formula F1. If I ask you question, when F1 will become false, tell me when F1 will become false. In which condition F1 will become false? Let me see the doubts. If anyone has any doubt, let me check. But you try this question. When will F1 become false? Neha, not in every case, in some situation, in at least one situation, they will be having different truth value in at least one situation. Okay, so not in every situation. For example, okay, let me focus on Neha's doubt. So Neha is saying that if two things, let's assume these two things, this is the first thing, this is the formula F1 and this is the formula F2. Let's look at these two formula. These two formula are not equivalent. We have seen this thing, that these two formula are not equivalent, because you can make their truth table. When you make their truth table, then the truth table of F1 will be 1101, the truth table of F2 will be 1011. Remember, this formula F1 is not equivalent to formula F2. Why? Because in at least one situation they are having different truth value. If you see this situation, when P is false, Q is true, in this situation F1, F2, they are having different truth value. That is why we are saying that F1, F2 are not equivalent, because in at least one situation, remember, in at least one situation they must have different truth value. But if you see this, in this situation they have same truth value. So remember, we are only focusing on at least one situation, okay, we are only focusing on at least one situation in which they have different truth value. Okay, so don't think that in all situations they should have different truth value. No, when two things are not equivalent, then in at least one situation they must have different truth value, only in at least one situation. Okay. Okay, so now someone is asking P unless Q. So let me also write it, P unless Q. Remember, in our mathematical logic, this unless will have same meaning as or. Unless is same as or. So when you write P unless Q, then this will mean P or Q. Okay, so take this point also. This unless means same as or. Similarly, like I told you, but is same as and. So this but is same as and. Similarly, this unless is same as or. Okay, is your doubt clear, Khusbu? This unless is same as or. So whenever you have this statement, P unless Q, then basically you are saying P or Q. Okay. Let me see if anyone has any other doubt. If you are asking any doubt, then you should write, before your doubt, you should write the word doubt, so that I know that who is asking a doubt, who is not asking a doubt. How but is used? Is it but is same as and, but is not same as if, but is same as and. I told you, whenever you see but, just replace it with and. Whenever you see unless, just replace it with or. There is no word until in our like until word is not used in our logic. In propositional logic we do not use until word. Okay, so this until is not a connective. Remember, this until is a English word. Not every English word we use in our mathematical logic. Okay, so until is not used in our mathematical logic. Okay, just because this until looks same as unless, don't this until we cannot use in our mathematical logic statements. Okay, don't worry about it. Now let's see the next point. So I asked you this question, this formula F1, P implies Q. When is this formula F1 false? So remember, if you see the truth table of P implies Q, yesterday also we have drawn this truth table. We have drawn this truth table many times, because if you remember, we have drawn this table many times. So remember, this P implies Q means this F1, because we are calling this F1. See, this formula is F1. This formula is this formula F1 means this P implies Q. Remember, this is true in all the cases. In all the cases, this F1 is true, except this case. This is the only case in which F1 is false. In which case F1 is false? When P is true and Q is false. When this is the situation, when P is true, Q is false, basically P is true and Q is false, in this situation this F1 will become false. In all other situation, remember, you see, in all other situation, this formula F1 is true. Okay, so what I can say that this F1 is false. This F1 is false. When it is false, it is false. It is false when P is true and Q is false. P is true and Q is false. P is true and Q is false. We can write it like this: P and Q bar. P is true and Q is false. We can write like this: P and Q bar. Okay, P and Q bar. This is how we can write it. So basically, when is P implies Q false, P must be true and Q must be false. And this statement, P must be true, Q must be false, this we can write like this: P and Q bar means P is true and Q is false. P is true and Q is false. Q dash means basically Q is false. So P is true and Q is false. Okay. Now you can check it whether this formula is equivalent to this formula. I leave it as a homework. You can check whether this formula is equivalent to this formula. This is the formula we have, this is the formula we have, whether they are equivalent or not. Let's leave it as homework. These slides I will share today. You can go through these slides and you can just check it out. Okay, and you can check whether they are equivalent or not. Let's leave it as a homework. Let's move on. So negating all these things, basically this thing is equivalent to this thing. So I told you that this thing, you can just make the truth table and you will see that they are equivalent. False, false, true, false, 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 true, false. The answer is also in the slide. All these things you already know. Now let's start our chapter, first order logic. This is the chapter that we will see now. First order logic, FOL, first order logic. This is also called predicate logic. The second name of this is predicate logic. So in your syllabus this name is given, predicate logic, but this is same as first order logic. Both things are same, first order logic, predicate logic. Okay, we will use this word first order logic, but remember both are same thing. Okay, what is first order logic? This first order logic, basically in first order logic what we do, we talk about objects. For example, if you remember propositional logic, if you remember, in propositional logic we are talking about propositions. We have proposition P, we have proposition Q, we have proposition R. We are talking about propositions. For example, this P proposition could be like my name is Deepak Punia. The Q proposition could be my name is Kapil. This R proposition could be my name is Sachin. So you can see these are different propositions. So this proposition can handle one object. Like for example, for me I can say that my name is Deepak Punia. For Sachin I can say that his name is Sachin. So but remember, the proposition cannot handle all the objects. If I say that all the students right now in this meeting, all the students right now are intelligent. If I say this statement, all students are intelligent. Now this statement cannot be captured by propositional logic, because this propositional logic has no facility to basically to capture this word all. Remember, this propositional logic can capture this. For example, this propositional logic can say that maybe Devika is intelligent, maybe Amandeep is intelligent. Okay, so individual elements, remember, for individual elements we can capture. Okay, Devika is intelligent, Khushbu is intelligent, Amandeep is intelligent, Neha is intelligent, and so on. So okay, so basically and also all these names I am just looking at the chat comment box, so don't think that I am not using your name. In the comment box right now these names are, I can see Nidhi, Mona, and so on. So you can, for each of them you can say individually that okay, Nidhi is intelligent, okay, Mona is intelligent, and so on. But remember, you cannot say that all are intelligent. So this propositional logic has no facility to capture this word all. Similarly, I cannot say that someone is intelligent, because this propositional logic has no facility to capture this word some. Okay, so propositional logic can capture each object individually, but it cannot capture all of them, it cannot capture some of them. This facility is not available in propositional logic. This facility is available in first order logic. So in first order logic we can talk about multiple objects and their properties. For example, all the almost 30 or 40 students who are present right now, 39 students are present. So this is the, let's assume this is the set of these 39 students. All you 39 students are in this set. This set we will call domain. This set we will call domain. Why? Because domain or universe, because right now we are only concerned about these students. Right now I am not concerned about what political party will win the next election. That is not my concern. Right now my concern is these 39 students. Okay, so these 39 students are my focus, are my concern. Okay, these are the people who are right now my universe. Okay, right now in my universe my mom is not there right now, because my focus, my domain right now is these 39 people. When I will be after this class, when I will be talking to my mom, at that time my universe will be my family. So you can see in different situations the universe can change. Right now our universe is these 39 students. Now I want to make a statement about these 39 students. What statement I want to make? I want to say all of these students are intelligent. So remember, this intelligent, being intelligent is a property. Okay, this is a property. And now when I am saying all students are intelligent, basically I am saying that for each student I am saying that he is intelligent, she is intelligent, he is intelligent, she is intelligent, and so on. For every student I am saying that you are intelligent, and so on. So basically in first order logic we can talk about multiple objects. Okay, and we can talk about their properties. This feature is not in propositional logic. So that's why this first order logic is more powerful than propositional logic. Remember, all the facilities that are in propositional logic, all the facilities, what are the facilities in propositional logic? The only few facilities in propositional logic are these: some propositional variable we have, okay, then we have some connectives we have, these kind of connectives we have, so some connectives. This is the only facility that propositional logic provides. But this first order logic provides all these facilities. Remember, this first order logic provides all these facilities, plus in addition to these facilities the first order logic provides more facilities, like this facility, this facility, this facility, these kind of I will talk about them, don't worry. I am going to talk about them. What are these facilities? Just like we talked about conjunction, just like we talked about disjunction, just like we talked about implication, we will talk about this, we will talk about this, we will talk about this. But these are the additional facilities that we have in first order logic. So it makes first order logic more powerful. Okay, so you can think of this propositional logic as a simple Nokia mobile, in which we do not have internet, the old generation mobile, Nokia mobile. So this has only very limited facility. This first order logic, you can think of it as a smartphone. In this you have internet, PUBG, whenever many things you have. Basically this first order logic has all the facilities of propositional logic, but some additional facilities are there. These additional facilities give this first order logic more power to talk about objects, to talk about universe, to talk about properties of objects and all these things. Let's see. So now let's start first order logic. Okay, so in first order logic basically we have these things: predicates. What is predicate? We will see predicate, we will see quantifier, we will see function. These three things, once we are done with these three things, this first order logic will be over. These three things we need to talk about. Let's talk about them one by one. So first we will talk about what is predicate. What is this predicate? So this predicate, to talk about predicate, this predicate is basically nothing but a property. This predicate is basically nothing but a property. For example, right now my domain, remember in first order logic we always need a domain. Domain means what objects are we concerned about. Right now my concern is these 39 students. So right now my domain is these 39 students. So these 39 students, so I can say Acadflix. The Acadflix students are right now my focus. So my universe is Acadflix students. So in this domain basically students are there. Now this is my domain. These Acadflix students are my domain. I call it domain, or I can call it universe. Okay, I can call it domain or universe. So now about these students, about these elements, because these are the elements in my domain right now, about these students I can make some statements. For example, I can make this statement: I of x. I of x means x is intelligent. Okay, x is intelligent, and so on. So now this is a property. Remember, x is intelligent. Being intelligent is a property. Okay, so I am saying I of x. Now this is a predicate. Yesterday also I told you that whenever we have this kind of a statement, x plus 2 equal to 4, this is not a proposition. Remember, this is not a proposition. We have already discussed yesterday. Why this is not a proposition? Because the truth value of this sentence will depend on x. When you change x, then truth value will change. So that's why this is not a proposition. Why? Because when you change x, basically, then you change the truth value of this sentence. Now similarly, this ix, x is intelligent, this is not a proposition. Why? Because the truth value of ix will change when we change x. Okay, let's assume that some students are more intelligent, some students are less intelligent. Anyway, so or you can assume that all students are intelligent. Basically, ix means x is intelligent. Now this is a property. Right now my domain is this. Remember, always focus on this domain, because this variable x will take values from this domain. This variable x will take values from this domain. So for example, in place of this x, I can replace maybe I can replace Devika. So it will become I of Devika. I of Devika will become Devika is intelligent. Okay, so this is a statement. Now this is a proposition. Devika is intelligent. Now this is a proposition, and the truth value of this proposition is true. So similarly, you can replace it with someone else, Amandeep, I of Amandeep. Then Amandeep is intelligent. Amandeep is intelligent. Now this is a proposition. Remember, as soon as this variable x takes some specific value from this domain, then now this I of Amandeep will become a proposition, because we can say true or false. So it is true. So this is how you can do it. For example, I can define a new predicate. Remember, this is a predicate. This is called predicate. For example, I can define a new predicate, f of x. X is female. Now you can see in this domain we have some male are there, some female are there. So you can see some elements, some students will satisfy this predicate, some students will not satisfy this predicate. For example, f of Devika is true, f of Amandeep is false. Okay, so you can see this is also a predicate. So this is how we define predicate. For example, we can take one more example. Let me take one more example. Right now my domain, let me take my domain to be set of natural number. What is set of natural number? You already know. Set of natural number means 1, 2, 3 and so on. This is the set of natural number. This is my domain right now. 1, 2, 3. These are my elements. Right now my focus is on these elements. This is my domain. So this is my domain. Now I can define few predicates, because remember, predicate are just properties, or you can say predicate are statements about the elements. Okay, the elements in this domain is 1, 2, 3. These are the elements in this domain. Predicate is nothing but a statement about these elements. For example, I can define a predicate E of x. X is even. So this is a statement about the elements in this domain, E of x. X is even. For example, this E of 1, this E of 1 is false, because 1 is not even. E of 2 is true. E of 3 is false. E of 4 is true. So you can see this is how different elements, when we replace this variable x, remember this variable x will take values from the domain. That's why this domain matters. This domain matters a lot. Okay, so if we change the domain, then the basically the values that this x can take, they will change. Okay, so this variable x will take values from this domain. So in this domain we have 1, so we can replace this x with 1. Similarly, in this domain we have 2, so we can replace this x with 2. Similarly, in this domain we have 3, so we can replace this x with 3, and so on. When we replace this x with 1, then we will get 1 is even. Of course, even means 1 is even. Now that is false, because 1 is not even. Similarly, when we replace this x with 2, then we will get E2. 2 is even. Of course 2 is even, so this is true. So this is how you can, this is a predicate, remember. Also remember that this predicate, right now here only one variable we have, but we can also have more than one variable. For example, we can have this predicate x comma y. Here we have two variables, and let's assume this predicate is x greater than y. So this predicate pxy, this has two variable. Also remember, because the domain is this is my domain, so both of these variables will take values from this domain. Okay, for example, this x can take value 1, this y can take value 1. Then what will be p11? P11 will be 1 greater than 1. Now that is false, so this p11 will become false. P21, what is P21? P21 means 2 greater than 1. So P21 will become true. Similarly, P12 will be 1 greater than 2. Now this is false. So right now this is a predicate because this is a statement about the elements in this domain, and this predicate is taking two variables. This predicate is on two variables. Okay, so basically these, or remember, once we fix our domain, then these variables can take values from this domain. So this x can take value from this domain, y can take values from this domain. So this is how this predicate can use more than two variables also. Like, it is not a necessary thing that predicate should be on one or two variable. You can also have predicate on three variable. For example, x, y, z. Let's assume this predicate is x plus y is equal to 2 z. X plus y is equal to z. This is a predicate on three variable. Now let's assume our domain I am giving you, my domain is 1, 2, 3. Let's assume 1, 2, 3. This is my domain. Okay, so if this is my domain, then what I can do, this x will take values from this domain, this y will take values from this domain, this z will take values from this domain. So remember, x can take value from this domain, maybe 1. This y can take value from domain, maybe 1. The z can take value from domain, maybe 2. Okay, so then what will happen? This P112, it will be 1 plus 1 equal to 2. Yes, this is true. So this P112, this will become true. Remember, this x cannot take 4y because 4 is not in the domain, and this variable x will take values from this domain. So this is not valid. Why? Because this x can only take values from the domain. So this x cannot take the value 4. This x can take value maybe 3, it can take. Maybe y can take 1, and maybe z can take 3. Then what will happen? 3 plus 3 is equal to 3. This is a false. So this P313, this will become false. So this is how we define predicate. Predicate is nothing but a statement about the elements of domain. So you need domain. Remember, first thing you need is domain. So first thing you need is domain. Then you have predicate, and in this predicate you can have any number of variables, but these variables will take values from this domain. All these variables will take values from this domain. So these variables can be replaced by the values in this domain. Okay, so this is the meaning of predicate. Now we will see the meaning of, okay, Amandeep is a female. Okay, sorry Amandeep. Okay, I apologize. I should not have taken such type of examples. Okay, sorry Amandeep, if you don't mind. Now let's see the next thing. The next thing we will see is quantifier. So I told you we will see some concepts. The first concept we have seen is predicate. Now the next concept that we will see is quantifier. We have two quantifiers. The one is for all quantifier, the another is there exist quantifier. Okay, so these two quantifiers we need to see. These are the two quantifiers in our syllabus. Let's see what is this for all quantifier. For all quantifier, this is known as for all. This is known as for all. Basically it is talking about all elements in the domain. Of course, again the same thing, you must have a domain. So you must have a domain. Let's assume this is your domain. Okay, so, and this for all is basically talking about all the elements in this domain. Okay, similarly, okay, first let's cover this for all. So this for all is saying that for every element in this domain, some predicate is true. For example, let's assume that this domain is set of natural number. Let's assume this is the domain set of natural number. So the elements in this domain is all the natural number, 1, 2, 3 and so on. These are the natural numbers in this domain. Let's assume this is our domain. Now, and let's assume that I define ex. This is a predicate I am defining. X is even. This is the predicate I am defining. This is the predicate. So we have seen what is domain, we have seen what is predicate. Now let's see what is quantifier. So if I write this statement, for all x ex, what it means? First let's see what it means. It means This, remember, first I will write this. This means for all. This means for all. Then this means for all x. Then this means ex is true. Ex is true. So remember, this is how we interpret it. For all x ex, how do we interpret it? One by one. Remember, one by one. First you interpret this. So this is for all. Then you interpret x. So for all x. Then you interpret this. Ex is true. So this statement, this formula, for all x ex, this formula is saying for all x in the domain. Remember, in the domain, because domain matters, because this x can take values from this domain only. Okay, so for all x in the domain, ex is true. Tell me, is this thing true? Is this statement, this statement, focus on this statement, is this statement true? Tell me, this statement is true or not? Yes, in predicate, as soon as you replace all the variables, then you will get a proposition. For example, in this ex, x is even. Now if I replace this x with some value from the domain, let's assume I replace this x with 4, then e of 4, that will become proposition. Okay, that will become proposition. So as soon as you replace all the variables of a predicate, then you will get a proposition. Okay, so yes, so you see this statement, for all x ex is true, this statement is, this claim is false. Why this claim is false? Because, for example, this 1 is not even, this 1 is not even, 3 is not even, 5 is not even, so this claim is false. So remember, this statement is false, means this is false. So you got it. You got the meaning of for all quantifier. This is the for all quantifier. Very intuitive thing. Remember, this is a very intuitive thing. This for all quantifier is basically talking about all elements of the domain, every element of the domain. Okay, so we are talking about every element of the domain. So let's take one more example. Let's take some more example we will take. Let's assume your domain. Let me give you your domain. Domain is set of natural number. You know what is set of natural number, 1, 2, 3 and so on. This is your domain. Now let me write the first statement. I am giving you a predicate. Let me give you a predicate e of x, and this e of x is okay, let me give you some other predicate, p of x. P of x is prime. X is prime. Now tell me, for all x px, what will be the truth value of this? What will be the truth value of this for all x px? Remember, this for all quantifier, this is talking about every element in the domain. This is focusing on all the elements. Okay, for all the elements in the domain, it is making a statement. Okay, so this for all x px, what it means? It means for all elements in the domain, px is true. This is the meaning of this. So this what is the meaning of this? The meaning of this is this: for all x in domain, for all x in domain, px is true. So this claim is false. Why? Because in the domain, you see, in the domain you have 4 is not prime, 6 is not prime, even 1 is not prime, 10 is not prime. So you can see this statement is false. So this formula is false. So this formula is false. Okay, this formula is false. Let me give you another formula. Let me give you another px, x is greater than 0. This is another predicate I am giving you, and now I am asking for all x px. Now tell me the truth value of this for all x px. Tell me the truth value of this. So you can try. The truth value of this is true. Why? because whatever, remember, for every element in the domain, this is true, this px is true. 1 is greater than 0, 2 is greater than 0, 3 is greater than 0. Every element in the domain is greater than 0, so it is true. Means for all x, px is true. This is true because every element is greater than 0, so this for all x px is true. So this is the meaning. And remember, when we change the domain, then the truth value may change. For example, let me change the domain. Now let me ask you third question. Now I am asking you third question, and the domain, I am giving you a different domain. The domain is set of real numbers, all the real numbers. You already know what is real number. Real number means all the positive number, negative number. For example, -1 is a real number, 0 is a real number, 1 is a real number, 1.3 is a real number, 1.333, this is a real number, and so on. These are the real numbers. So the domain is basically set of all real numbers. Now the px is same. Px means x greater than 0. Now tell me, for all x px, what will be the truth value of this? What will be the truth value of this for all x px? What will be the truth value of this? So the truth value of this will be false. Why? Because now our domain has changed. Remember, this for all quantifier, it is talking about all the elements of domain. If you change the domain, then basically its universe will change. Okay, so now it is talking about all the real numbers. So of course, if, for example, this -1, this is not greater than 0. So for this -1, this px has become false. So this complete thing, for all x px, this will become false. Okay, remember, this for all quantifier is talking about all the elements in the domain. Now let's see the next quantifier, there exists quantifier. What is this quantifier? This is there exists quantifier. There exists quantifier. This quantifier is talking about at least one element. Remember, it is only interested in at least one element. Okay, it is only interested in at least one element. This quantifier is not interested in all the elements, it is interested in at least one element. As soon as it will find at least one element, it is happy. Remember, this for all quantifier is concerned about all the elements. Okay, but this quantifier is concerned about at least one element. This there exists quantifier will become happy as soon as he will find at least one element which satisfies a predicate. But this for all quantifier, he will be happy when all elements in the domain satisfy the predicate. Okay, so what do we, when we write like this, there exists x px, when we write like this, what do we mean? We mean, first of all, you will read this. What it is? It is there exists x. There exists x in the domain. Of course, in the domain. You don't need to write it. Why? Because always x will take values from the domain. So you have already fixed the domain. Let's assume you have already fixed the domain. Then you will say there exists x in the domain such that p of x is true. So remember, this there exists quantifier, this is only interested in at least one element. As soon as he will find at least one element in the domain who satisfy px, he will be happy, means he will be true. If this there exists quantifier, if he cannot find any element in the domain who satisfy px, then he will be said basically he will be false. For example, let's take this situation. Let's take the domain to be set of natural number. This is the domain 1, 2, 3 and so on. This is the domain, set of natural number. This is the domain we have, and let me define predicate px. The predicate is x is even. This is the predicate we have. Tell me the truth value of there exists x px. What will be the truth value of there exists x px? the truth value of there exists x px. What will be the truth value? So the truth value will be true. Why? Because see, this there exists quantifier, he is only looking for at least one element. As soon as he will find at least one element who satisfy px, he will be happy, he will be true. So what he will do, he will check elements one by one. First he will check this. Okay, he is not this one is not satisfying. This 2 is satisfying because 2 is even. So this 2 is satisfying. Now this there exists quantifier does not care about other elements. Why? Because as soon as he will find one element, at least one element, as soon as he will find who satisfy px, then he will become true. So this there exists x px will become true. Why? Because p2 is true. So we are only interested in at least one element. This is the only thing we are interested in. Let's take one more example. Let's assume that domain, our domain I am giving you a set of natural number, the same domain I am giving you set of natural number, and my question now first predicate that I am having, predicate x, this is x less than 0. This is my predicate. Now tell me there exists x px. What will be the truth value of there exists x px? What will be the truth value of there exists x px? So you can try. The truth value of this there exists x px will be false. Why? Because see what this will do, this there exists, what it will do, he will go, this there exists quantifier, he will go tok, 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 he will go, he is going, and now he is going and checking, he is interested in finding at least one element. So he only wants to find at least one element. So he will check, this 1 is not satisfying because 1 is not less than 0, 2 is not satisfying, 3 is not satisfying, 4 is not satisfying, and so on. So you can see no element is satisfying. So this there exists quantifier, he is standing here. Now this there exists quantifier cannot find at least one element who will satisfy px. So he will become sad, basically he will become false. So this there exists x px will become false. Now try this question, there exists x not px. What will be the truth value of this? There exists x not px. What will be the truth value of there exists x not px? So you can try. The truth value of this will be true. The truth value of this will be true. Remember, see, this statement is saying there exists x for whom this thing is true. Remember, this is like this. There exists x for whom this thing is true. What is this thing? This is negation of px. So if you see for this element 1, this negation of p1 is true. Why? Because negation, see, p1 is false. Why? 1 is less than 0, this is false. So p1 is false, and negation of false is true. So for this one, this negation of p1 will become true. So this 1 is satisfying this property. This 1 is satisfying this property. So you can say, and we are only interested in at least one element, so we will say true. So this there exists x negation of px, this will become true. So what is the conclusion that we got? Let's see some conclusions. Now I am going to give you some conclusions right now. First I will give you the conclusion. If you have a statement this for all x px, if you have this statement, let's assume the domain is D. Let's assume the domain is important. Remember, Okay, the domain is very important. So let's assume domain is D. So you have this statement for all x px. So it will become true. When will it become true? When this will become true? This will become true when for each element, remember, for each element in domain is D. For each element in domain, px must be true. This thing must be true. So in that case, this will become true. Now the second point is, there exists x px. When it will become true? Let's assume the domain is D. The domain is D. When will this become true? It will become true when for at least one element. We are only interested in at least one element. You must find at least one element. So at least one element in domain. For at least one element in domain, let's assume that element is E. So for at least one element E in domain, basically PE must be true. For at least one element you must find. Now the third thing, when will this become false? This thing for all x px, when will this become false? See this for all x px, it will become true when for every element it is becoming true. Okay, so when will it become false? It will become false when for at least one element this px is false. So I can say like this: for at least one element in D, let's assume that element, at least one element you need to find. Let's assume that element is E. So for at least one element in domain, basically P must be false. In this case, this for all x px will become false, right? The fourth thing, when will this become false? When will this thing become false? This there exists x px. When will it become false? See, this there exists px, this is becoming true when you are finding at least one element in the domain for which px is true. Now let's see when it will become false. It will become false when you cannot find at least one element in the domain. Basically you are searching the complete domain, but you cannot find any element. In the domain for which px is true. What it means? It means for all elements in the domain px is false. So basically what it means for all elements in domain in D, basically for all elements in the domain px is false. Okay, for all elements in the domain px is false, because if for all elements in the domain if px is false, then what it means? It means there is no element for which px is true. Okay, so that's why this there exists x px will become false. So these are the four very important cases. Remember, when this will become true, when this will become true, when this will become false, when this will become false. Let's move on. And so we have seen predicate, we have seen quantifiers, we will see function when we will solve example. At that time we will see. So actually the first order logic is over. I told you the first order logic has these additional facilities. We have seen these additional facilities. Now the first order logic is over. Now we will see some concepts. Okay, now remember the difference between let me just go through all these slides, because all these slides I have already discussed. So I told you, if you remember, I told you in the beginning of the class that in propositional logic, remember, in the propositional logic, we have propositions, P, Q, R. These are propositions, and each proposition can either take true or it can take false. This is the universe of a proposition. Remember, this is the universe of a proposition, because a proposition variable, this P is a proposition variable, Q is a proposition variable. Any proposition variable can take either true or it can take false. These are the only two values. One of them it can take. For example, maybe this P is taking true, this R is taking true, Q is taking false, S is taking false. This can happen. Basically these are propositional variable and they can take either true or they can take false. For example, let's assume this is the propositional logic formula. Let's call it formula F1. This is the formula F1 you have. This is the formula F1 you have. In this formula F1, let's assume this situation. Let's assume that this P is taking true, R is taking true, Q is taking false, S is taking false, then what will be the truth value of F1? Quickly try this question. What will be the truth value of F1? Tell me the truth value of F1. What will be it? True or false? Truth value of F1. Try this question. What will be the truth value of F1? So in the same question we can apply two concepts. The first concept is, remember the precedence. I told you that negation has the highest precedence, so you do the negation first. The negation has the highest precedence, then this conjunction has highest precedence, then this disjunction has highest precedence. Finally you will do the at the end you will do the implication. So what is P and Q? P is taking true, Q is taking false. So what will be P and Q? P and Q will be false. Now actually you don't even need to solve this for why, because see, this is becoming false. False implies anything. Do not care. I do not care. Remember, now I do not care about it. Why? Because this LHS of the implication is false. So automatically this complete thing will become true. I told you, whenever you have implication, you have LHS, you have RHS. If LHS itself is false, then this complete implication will become true. This we already know. So this will become true. So you can see in this situation, when P is taking true, R is taking true, Q is taking false, S is taking false, in this situation this formula will become true. This formula will become true. But the important thing here is that in propositional logic we have propositional variables. These propositional variable can take either true or they can take false. They cannot take, for example, this propositional variable P cannot take 1. Okay, this cannot take 2. This propositional variable can either take true, or this propositional variable either can take false. This propositional variable cannot take 3. So that's why we are saying that any propositional variable can only take either true or false. So this is the universe of propositional variable. Now in first order logic, remember, in all these are the properties of propositional logic. We have already seen all these things. Anyway, so in first order logic what will happen? In first order logic we have something called universe. Maybe our universe is, if our universe is solar system, let's assume, then in our solar system we have these things we have basically. Okay, so in first order logic we talk about universe, we talk about elements of a domain. If our domain is solar system, then we will talk about earth, we will talk about a moon, many other things. Okay, don't judge my general knowledge. So anyway, but the thing is, in first order logic we talk about a universe. Okay, and you can see when we were talking about one, let's assume this was our set of natural number. This is our domain. Let's assume this is our universe. Then at that time, our variable, if you remember, our variable was taking values from this domain. So this variable x could take value 3. This variable x could take value 4. Okay, so you can see in our first order logic, these variables can take values from the domain. So our universe can be anything. In propositional logic, our universe is only true, false. That is only our universe. But in first order logic, our universe can be anything. And when our universe can be anything, then our variable also can take value from that universe. Now, first order logic, in first order logic, basically, the first thing is, we are talking about some universe. That universe is called domain of discourse. This is just a name, okay? Domain or universe. So our variables will take values from that domain. So the domain is important. Next thing we have is something called predicate. I have already defined what is predicate, and predicate can take any number of variables. For example, this is a predicate on 1 variable, this is a predicate on 2 variable, this is a predicate on 3 variable, and so on. So you can see this predicate, this is a predicate, and so on. So how many number of arguments it is taking, that is called arity. For example, this predicate is taking one argument, one variable. So this predicate has arity 1, this predicate has arity 2, this predicate has arity 3. Okay, so our predicate can take any number of arguments. Okay, and the number of arguments, the number of variables in our predicate is called arity of that predicate. Anyway, so we have seen the concept of predicate. Next, now basically, if you remember in propositional logic, what we were doing, we were converting a English statement into propositional logic formula. We had an English statement, we were converting that into propositional logic formula. Now what we will do, now we will take English statement and we will convert it into first order logic formula. Okay, so now what, for example, this kind of English statement, this is an English statement: for any natural number n is even if and only if n square is even. This is a predicate logic formula. Okay, this is an English statement and we want to convert this into predicate logic formula. So for that we need some tools. Those tools are predicate, quantifiers. These are the tools. We have already studied those tools, and at the end we will see how to convert this statement into first order logic formula. So we have seen something called quantifier. There are two quantifiers, and for all quantifier, and there exists quantifier. All these slides I will share with you. Don't read these slides. Okay, right now if someone is reading all these slides, okay, don't read them. I have already discussed everything in these slides, so there is nothing, there is no need to read these slides. I will share all these slides with you, don't worry. Okay, now basically we will now we will see how to convert an English statement into first order logic formula. This we will see at the end. Okay, right now we won't see it, right? At the end we will see it, don't worry about it. I will come back to this example. So we have something called universal quantifier. I have already told you what is a universal quantifier. Whenever we have this kind of formula for all x, and there is something here, okay, anything could be here, let's assume here we have chi. So basically this says that for all element x, for all element in the domain, because this variable x should take value from some domain, so you must give me a domain. So let's assume you have a domain. So this for all x chi, what it is saying? It is saying that for every element in the domain, this thing must be true. Okay, so this is universal quantifier. And then we have we will see this kind of a statement also. We will convert this kind of a statement into first order logic formula. Don't worry, at the end we will do it. So let's see what is there exists quantifier. We have already seen what is there exists quantifier. There exists x chi. What it means? It means, of course you must have domain. So it is basically saying that there exists an element in the domain for which this chi is true. This is our existential quantifier. There exists quantifier. All these things we have already seen. So I am just quickly going through this slide. Now let's see the precedence order. The precedence order we have already seen in propositional logic. The precedence order we have already seen in the propositional logic. But in propositional logic we did not have for all there exist. These things we did not have in propositional logic. If we include these in our table, if you remember the order was like this: negation, then we have conjunction, then we have disjunction, then we have implication, then we have by implication. This was the order, remember? Now if we include for all there exist, if we include these things, then the order will be like this. The top order will be, the top order basically will be these things. There exist, they basically are on the same level. These are on the same level. Okay, so you can see this, for this quantifier, they have more precedence than these operations. So this is the order. Okay, what do I mean by it? Let me take this example: for all x, px and qx. What it means? For all x, p and q. Let's assume p and q. Okay, wait a second. So the order is like this: negation, for all there exist, they are on the same level. Then we have conjunction, disjunction, implication, by implication. This is the order. And now let me tell you this: for all x, let's assume chi and phi. Let's assume this is our statement. Then how should I interpret it? There are two ways to interpret it. The one way is to interpret like this. The another way is to interpret like this. What is the correct way? The correct way is this. Why? Because you can see this for all quantifier has more precedence than conjunction. So you must give this for all more precedence than conjunction. So this for all has more priority than this conjunction. So you should not do conjunction first. First you should do the for all. then you should do the conjunction. So this is what we mean by priority or precedence. For example, you can take this example: for all x p or q, if this formula you have, then basically it means that this you will do first. Why? Because this for all quantifier has more precedence than disjunction. Okay, so this is the meaning of precedence. So for example, if you have this formula, let's assume you have this formula: for all x px or rx implies qx. Let's assume this is the formula. Then how will you interpret it? Remember, this for all x has higher precedence than this disjunction, so you will not do disjunction first. First you will do this for all. Then you know that this disjunction has more precedence than this implication, so next you will do this. Then at the end you will do the implication. This is the meaning of precedence. So remember, this quantifier for all there exists. These quantifier are basically have the almost same precedence as negation. Okay, so this is the precedence order. Now we will see nested quantifiers. Let me see if anyone has any doubt. Let me see if anyone has any doubt. Okay, so if anyone has any doubt, then you can ask in the comment box. Let me just see if anyone has any doubt. Okay, so no one has any doubt. Then actually the time is almost over, so we need some more time to finish the remaining things. Shall I take half an hour more? Can I take half an hour more? Either we can take half an hour more right now, or we can see the remaining topics. Maybe half hour session we can have tomorrow. Your wish. Okay, we should wind up now. Okay, so let's see the if anyone has to go, then you can watch the recording also. The recording are also available, so you can watch the recording also if you have to go. Let me wind up this first order logic. The next thing that we have is nested quantifier. Remember, so far we were seeing only individual quantifier. For example, these kind of statements we were seeing: for all x px, there exists x px. So here only we have single quantifier. You can see we have single quantifier here. Okay, we do not have nested quantifier. For example, now we will see this kind of statement: for all x, for all y, pxy. Similarly, we will see there exists x, there exists y, pxy. These kind of statements we will see: for all x, there exists y, pxy. These kind of statements we are going to see: there exists x, for all y, pxy. So these are known as nested quantifier. Nested quantifier. Okay, let's see this concept of nested quantifier. So first of all, we will see what it means. What this means: for all x, for all y, pxy. What it means? Let's assume your domain is D. Let's assume the domain is D. So the domain is D. So this x is taking values from D. This y is taking value from D because the domain is D. Okay, so this x is taking value from D. This y is taking value from the D. Let's assume in the domain we have these elements. Then what it means? It means for all x, for all y, pxy is true. It means for all x, for all y, pxy is true. So basically it means like this: this x can take this value, this x can take this value. So if x takes this value, now y can take this value, this value, this value, this value. So for all these pairs, let's assume this value is a, this value is a, b, c, d. So basically for all these pairs, a comma a, a comma b, a comma c, a comma d, for all these pairs this pxy must be true. Similarly this x can take b, this x can take c, this x can take d. Remember, basically for all pairs, all the pairs that are possible, all pairs, for example b comma a, b comma b, b comma c, b comma d, for all these pairs, for all similarly c comma a, c comma b, and so on. So whatever pair is possible, remember, whatever pair is possible, whatever element here, whatever, for all these pairs this px must be true. This is the meaning of for all x, for all y. So the meaning of for all x, for all y is for all x, for all y, pxy. The meaning of this is for all pair, the value is coming from domain, for all such pairs this py, so I can say for all such pairs this pxy must be true. Let's take one example. Let's assume the domain is a set of natural number. This is your domain 1 2 3 and so on. So this is the set of natural number you have, and let's assume that this pxy is x greater than y. Okay, now I am writing for all x, for all y, pxy. Tell me what is the truth value of this. Try this quickly. What is the truth value of this? Prerna, the domain for x comma y, they can be different also. So what we will do right now, don't worry about the right now, just focus that domain is same. Okay, we will take some examples, 1 or 2 examples, when we will solve the previous year NET questions of mathematical logic. At that time we will take some example where x and y have different domain. Right now don't worry about all these things, I will cover everything, don't worry. So this point that you have written, this point we will cover when we will discuss the previous year NET questions of mathematical logic. Okay, so this is false. Why? Because you remember this for all x, for all y, this is saying that for all pair this pxy must be true. But if you see, this is for example, let's take this pair 1, 2. Let's take this pair. For this pair you can see this is not true. So for this pair 1, 2, this pxy is not true. So you can say that this will become false. You can also take this pair also, 1, 1 also you can take, because for this pair 1, 1, this 1 greater than 1, this is also false. So we have found at least one pair for which this pxy is false, so we can say that this is false. Why? Because this for all x, for all y, this will become true when for every pair this pxy is true. Okay, and I am repeating it again. Actually we should wind up this first order logic today, so that we can start so that we are not behind the schedule. We already have a schedule and we want to follow that schedule, so that's why I am winding it up today. And if you have to go, then what you can do, you this half an hour you can watch the recording. If you have any doubt, then you can ask in the on the group, you can ask, you individually you can ask me. So we are not your doubts are not we are going to cover all your doubts. Okay, so don't worry that your doubt will not be cleared. I will clear all your doubts. Okay, so let's see the next thing. The next thing is there exists x, there exists y, pxy. What it is saying? It is basically saying that there exists x, there exists y, means basically like this. In the domain there exists a element, means for at least one pair. So I can say for at least one pair, I only need at least one pair. For at least one pair this must be true. Okay, let's take the same example. The domain is natural number, set of natural number. The statement is pxy x greater than y. Now tell me what is the truth value of there exists x, there exists y, pxy. What is the truth value of this? Tell me. So I just want to follow the schedule, and that's why, because we are taking examples and many things, so that's why I am taking time to explain all these concepts. That's why it is taking time. So let's take half an hour more. If you have to go, then you can re-watch this half an hour, re-watch this recording, and if you get any doubt, then you can ask individually on the WhatsApp. You can ask me directly on the WhatsApp. Okay, you can send your message and I will answer it. So yes, it is true. Why? Because you need only at least one pair. So okay, for this pair you can take this pair. For this pair 4 greater than 2, so for this pair pxy is true. For this pair 4,2, so you need at least one pair. Only one pair you need, at least one pair you need. So as soon as you find at least one pair, then that's it, this will become true. So these two nested quantifier we have seen. The next quantifier are more tricky, so you need to focus here. You need to put all your focus here. What is there exists x for all y pxy? What it's saying? It is saying like this: there exists x. First of all, there must exist x. There is a domain and there must exist a x. Now for this x you take all the values in y. This is the meaning. Remember, this is the meaning. There exists x for all y means first you find x, first you find at least one value here, first you find at least one value here. Now for this value you take all the elements in the domain, you take all the elements in the domain. Now for all these pairs, let's assume this is value e, let's assume this is the value, this element has the value e. So basically we are saying that for all these pairs you can put anything here, you can put anything here, anything here. Okay, for example e comma e, e comma a, e comma b, e comma c. For all these pairs, for all these type of pair where this first element is e, this first element is fixed, for all these type of pair this pxy must be true. Did you get it? There exists x for all y means first of all there must exist. So first of all you must find at least one element. Let's assume you found e. Now for this e, you take all the elements. Basically these kind of pairs you can take, and for all these kind of pairs pxy must be true. This is the meaning. Let's take one example. The same example we are going to take. This is our set of natural number, and now my predicate px is x, pxy is x greater than y. This is my pxy. Now tell me, for there exists x for all y pxy. Now tell me about this. What is the truth value of this? Tell me truth value of this. Truth value of this. Okay. Let's see. Don't worry. See, this pxy is x greater than y. Okay, and this set of natural number is the domain. So this x will take values from the domain. So this is the domain you have. This is the domain you have. This y will take values from the domain. So this is the domain you have. I am telling you this there exists x for all y. It is saying that you must find at least one value. At least one value you must find, such that at least one value you must find such that with this value you take any value. Okay, you take any value here. For these kind of pairs this pxy must be true. For these kind of pairs this pxy must be true. So can you find it? So actually you cannot find it. Why? Because whatever value you take, for example you take 1, then for this 1 comma 1 is not true. You take 2, for this 2 comma 2 is not true. You take 3, for this 3 comma 3 is not true. So whatever value you take, whatever value you take, for that value for this pair e comma e, p e comma e will be false. So you can see you cannot do this. Are you getting my point? I am saying that you find me at least one value, whatever value. It is your choice, but just find me at least one value. For that value, let's assume that value is 3. Now with this value you take all the values. With this 3 you take 1, with this 3 you take 2, with this 3 you take 3, with this 3 you take 4, and so on. With this 3 you take all the values. For all these pairs pxy must be true. Pxy must be true. This is what I mean. Okay, so you can see you cannot find any for this example you cannot find any such pair. Okay, because whatever value you take, whatever value e you take, whatever value e you fix here, okay, you can see e comma e, this pair will not satisfy pxy. Okay, so we can take one more example. This is confusing, I am telling you this is confusing. So let's take one more example. Let's assume our domain is same, set of natural numbers, and I am giving you pxy, and this pxy is x is less than or equal to y. This is pxy. Now tell me there exists x for all y pxy. Now tell me the truth value of this. Now tell me the truth value of this. Try this question. Try this question. So yes, it is true now. Why? Because remember, I can find at least one value. At least one value. What value I can find? For example, I can find 1. For example, I can find 1. Now, with this one, whatever value I put, for example, I put 1 comma 1, I put 1 comma 2, I can put 1 comma 3, and so on. Whatever value I took. So I have found at least one value I have found. That value is 1. At least one value I need. Okay, and at least one value I need, and that value is 1. I have found it. Such that with this 1 you take all the values. For all these pairs, this pxy must be true. You can see 1 is less than or equal to 1, 1 is less than or equal to 2, 1 is less than or equal to 3, and so on. So that's why this is true. So this is true. Anyone has any doubt? Previous example, Prerna, which example are you asking? You just focus on this example. In the last example, I told you that whatever element you take, because in our last example our pxy was this. Our pxy was this, x greater than y. This was our pxy in last example. So you take whatever value you take, you can see that when you pair this element with itself, then it will become false. So basically, that's why in our last example I cannot find that at least one value. I cannot find that at least one value. But in this example, I can find that at least one value. That at least one value is 1 itself. So 1 1 1 2 1 3, all these, for all these pairs, this pxy is becoming true. So that's why this has become true. You can think of this. Okay, let me tell you how can you think of this. There exists for all y pxy. How can you think like this? This you can think like this. This is basically like there exists an element such that this element with all these elements pxy is becoming true. So like there is someone such that for everyone this pxy is true. For example, this x is like God. This x is like God maybe. Okay, because God is for everyone, right? So that's why you can take it. If you believe in God, then you can take it as a God. If you do not believe in God, then you can take it as a Sachin Tendulkar or any. So basically this is the analogy, that it is saying that you must find at least one person, at least one element you must find, such that whatever element you put, for example, this could be Mahatma Buddha, because Mahatma Buddha had sympathy, compassion for everyone. So if this is Mahatma Buddha, now you put any criminal or good man, bad man, whatever you put here, this Mahatma Buddha will have compassion for everyone. So basically you must find me at least one element such that, you must find me such that with this element you put any element, with this element you put any element. Now for these kind of pairs, our pxy statement must be true. Okay, so Nidhi, second last example, I am not getting your doubt. Let's do one thing. If you have any doubt, you can ask on the WhatsApp, on the group, you can ask your specific doubt. Now the last thing that is remaining is this quantifier. For all x, there exists y, pxy. This quantifier is remaining. This nested quantifier is remaining. Okay, so this is the quantifier that is remaining. Let's see this. What it is saying? It is saying like this. Remember, this for all. So for all means for everyone, for this, for this, for this, for this, for this, and so on. This is saying there exists. There exists means, so okay, let's go one by one. One by one we will go. First you focus on this for all. So this for all is saying that for everyone, for him, for her, for him, for it, and so on. So for everyone. Now for everyone there must exist someone. 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 Basically, for everyone there must exist someone such that pxy is true. Remember, don't think like this. This for all x there exists y. This means that for everyone there is someone. This does not mean this. Some students do this mistake. What they think? They think like this. For everyone there is a fixed element. No, this is not what we are saying. This is not what we are saying. We are saying that for everyone there must be someone. For example, you can think, if you want to understand it, you can understand like this. There is a song, there is a Rabata song, there is this Bollywood song, Rabata song. Okay, in this song there is a line that for जहाँ में खुदा ने सभी के लिए किसी न किसी को बनाया है हर किसी के लिए. So there is a line, there is a statement here. So that statement is basically saying that for everyone there is someone. That statement is saying that for everyone there is someone. That is the statement. There is someone. Okay. कहते हैं इस जहाँ में सभी के लिए किसी न किसी को है बनाया हर किसी के लिए. Something like that. Okay. So there is this song. Actually, you can think of this for all x there exists pxy. You can think of this as this song. For everyone there is someone. Okay. Different people can have different. Okay. So that is the meaning here. Now you can take, for example, let's take one example. Let's take for all x there exists y pxy. Let's take this. Now pxy I am giving you pxy as pxy I am giving you x greater than equal to y. This is the pxy I am giving you. And now the domain is set of natural number. This is the domain 1, 2, 3 and so on. This is the domain. And now you tell me what is the truth value of this. Tell me truth value of this. No, Khushbu, that is not one-to-one mapping. No, Khushbu, you are getting incorrect impression. I am saying that for everyone there must be someone. For example, for this A, there must be someone. For this B, you can have this. Okay, no problem. Because for everyone you must have someone. Okay, for everyone. For C, the only thing I am interested in is that for everyone I must find someone. Maybe everyone has same person. Maybe everyone has same person. For example, maybe all these are Pandav. Maybe Pandav, okay, Yudhishthir, Bhim, Arjun, Nakul, Sahdev. These are the Pandav, and this is the Draupadi. So this is also okay. But I am saying this is also okay. This is also okay. Okay, and this is also okay. Basically, for everyone there must be someone. That is the only thing we are interested in. For different people, we can have different people, or we can have same people. We do not care. For everyone there must be someone. Okay. Anyway, this is just an analogy. Don't this is just analogy for understanding. Okay. I am just saying that for everyone you must have someone. That's the only point. Now let's see what is the truth value of this. The truth value of this is true. Why? Because for everyone there is someone. For everyone, for one there is, you can see, for one there is one. Okay, for one there is one. For two there is, for the twos there is one. Remember, for two there is one also. We are only interested that for everyone there must be at least one. Okay. Everyone, for everyone, like this situation will also work. Like this, let's assume there are two people here. This situation will also work. because we are only interested in that everyone must have at least one. Everyone must have at least one. This situation will also work. Okay. So for everyone there must be, yes, Neha is correct. For everyone there is at least one. So for example, this 1 is having 1, this 2 is having 2, 3 is having 2, 4 is having 2, 5 is having 2, 6 is having 2, 7 is having 7, 8 is having 8, 9 is having 9, and so on. So everyone has someone. So basically everyone has that's why this is true. That's why this is true. Let me ask you one more question. Now the pxy I am giving you is x greater than y. Okay, x greater than y, and the set of natural number, this is the set of natural number. Now tell me, for all x there exists y pxy. Now tell me the truth value of this. Tell me the truth value of this. Okay, that's why actually I like watching movies. I take many references from movies. When I will be teaching compiler design, at that time I will give a reference of the movie. There is a Sanjay Dutt movie, Luck. So the complete parser actually can be explained, all the parser, bottom up parser, top down parser, all the parser, LR0 parser, LR1 parser, SLR1 parser, the complete parsers, this complete chapter can be explained by the movie Luck. There is a movie Luck. I can explain this complete parser with only help of this Luck movie. You will never forget these parsers, because this is a huge chapter. This parser, this is a huge chapter. This complete chapter can be explained by this movie Luck. Sanjay Dutt movie is there, Luck. Anyway, so these things help you in understanding concept, and these things help you in remembering the concept for a longer time. So you must also create some images in your mind. For every concept you must create some images, some story you must create. You can create your own story, I do not care. You must create some story so that you can remember all the concepts for a very long time. Most of the subjects I remember by some story. I can teach the complete algorithm subject by some story. But anyway, okay, so this will help you. Okay, this will help you basically. Okay, we will see it. I will definitely the compiler design right now in the crash course. When we are studying the crash course, at that time compiler design will be taught by, I think, Abdul sir. But when we will study this complete course, okay, right now we are studying crash course for 45 days, but after this crash course we will start complete course. In that complete course we will see every single thing in a detailed fashion. There I will teach compiler design. This compiler design subject I will teach, and this compiler design, this complete subject we will see with a story. So a complete story we will see. A receptionist, a hotel story we will see. There is a receptionist. This receptionist is basically lexical analyzer. Then we go to parser. In that parser we will see the story of Luck, movie Luck, and so on. So this compiler design subject actually you can remember by one story, one very nice story, one very nice flow, and the complete compiler design subject will be over. Anyway, let's come to this example. This is false. Why this is false? Because see, 2 has someone, 2 has 1, 3 has someone, 3 has 2, 4 has someone, 4 has 1, 5 has someone. You only need to find at least one, for every one you need to find at least one element. But who is there for 1? Who is there for 1? There is no one for 1. You can see there is no one for 1. This 1 is all alone. He is forever alone. Okay, there is no one for 1, because if you take x, if you take in place of x, if you take 1, then this 1 is not greater than anyone, whatever value. Even मतलब 1 के लिए तो 1 भी नहीं है. ओके, ये खुद का सगा नहीं है, मतलब एक तरीके से आप ऐसे समझ सकते हो कि there is no one for 1. Okay, so that's why this statement is false. Why? Because everyone must have someone. This 1 has no one. This 1 is alone. This one doesn't have even 1 in himself. Okay, so that's why. Okay, so let's see. Yes, Mona, the TOC subject also we can study in a very nice story fashion, where terrorists are the strings, the rejected strings are terrorists. Anyway, okay, we will see. TOC we will study in complete course. In crash course also we will study TOC, but in crash course we do not have time for these stories. But in complete course we will see the complete subject in a story wise manner. So anyway, did you get it, this point, that this is false? Why? Because 1 has no 1. For this 1, no one is there. Yes, everyone wants rank 1. Okay, next. Let's see. So these statements, remember, in these slides I have mentioned, for all x there exists x p x y. Basically it is saying that for any choice of x, whatever choice you take for x, there must be some choice for y. Different x can have different choice. Okay, different x can have different choice, same choice, I do not care. Different x can have many choices, I do not care. But for every choice of x, you must find at least one choice for y. Similarly here, there exists y for all x. It is saying basically there must be a fix, there must be at least one y, there must be at least one y, such that you put anything here, you put any choice here, so this pxy must be true. Now let's see the next thing. Remember, order matters. In quantifiers, order matters. For example, this thing is different from this thing. These two things are different. I told you these two things are different. This is saying that there must be at least one, such that, for example, maybe APJ Abdul Kalam, because when you put APJ Abdul Kalam here, then you can put any Indian here, any Indian, every Indian loves him. So you can think like this, maybe, okay, maybe. Or this for all x there, this is saying that everyone loves someone, everyone has someone, everyone has the support of someone. Okay, everyone has the support of someone. Anyway, so now how to translate English statement into mathematical logic formula? Whenever you have this kind of statement, let me give you the template. This template is very, very important. You can mark star here, 5 star, 6 star, 7, whatever number of star you have, the whole star of the complete galaxy you can put here. But this is very important thing. When you have English statement of this form, now I am giving you an English statement. This form, for all x, for all x, for all x, Sx implies, wait a second. So whenever we have this kind of a statement, for all x, satisfies px. Let's assume this is this kind of statement. If you have, let's assume this kind of statement, if you have, for all x, Sx satisfies px. If you have this kind of statement, then how will you translate it in mathematical logic? Very easy. This you will translate like the for all x. This you will translate like this: Sx implies px. Remember this thing. Right now we are studying crash course, so I am not giving you proof of this thing. Why this happens? In complete course, I will focus on this thing for a very long time. Okay, I will give you proof. I will give you why this is correct, why this is not correct. All these things I will give you. Don't worry. But this trick you can remember, that whenever you have English statement of this form, for all x, Sx satisfies px. If this is an English statement you have, then you can convert this English statement like this: for all x, Sx implies px. Remember, with for all quantifier you use implication. With for all quantifier you use implication. This is the idea. Also, if you have this kind of statement, let's assume your English statement is this: for some, you already know what is for some means there exist. This means there exist. This means there exist. There exist. For some means there exist. Or you can say for at least one. Or you can say for at least one. All these things are same. For at least one. All these things are same. For some there exist. For at least one. All these things are same. Sx satisfies px. Sx satisfies px. How will you translate it? You will translate like this: there exists x such that Sx and px. Remember, there exists quantifier. With this quantifier we use conjunction. With this quantifier, for all quantifier we use implication. Okay, and with there exists quantifier we use conjunction. Remember this thing. Let's take one example. I told you one example. There was a velociraptor example I was taking, so we can take that example. Some velociraptor, okay, let's call it velo. Some velo can open the okay, let's not take that example. We can take simple example and you can do it. So I can take this example. Some student knows discrete mathematics. Let's assume the domain is not given. Remember, whenever domain is not given, then you should consider everything in the domain. For example, if domain is not given, then consider the domain to be set of all elements, set of all people. Every people is here, every person is here, every element is here, every number is here, every alien is here. Okay, every single thing is here, every plant is here, everything. When domain is not given, then you should think that the domain consists everything. Whenever domain is not given, at that time you can think of domain as the complete multiverse. All the things are there that are there, you can think of them in your domain when domain is not given. So this kind of statement, some student knows discrete mathematics. How can you write this statement in first order logic? See, this statement basically saying that some student, I can write like this: for some student. I am just basically converting this statement in our setting. I told you we have a setting. What is that setting? That setting is like this: for some student knows discrete mathematics. What it means? It means if basically if X is student, means Sx means X is student, satisfies DMX. This Sx means X is student, DMX means X knows discrete mathematics. Okay, so this Sx means X is student, okay, and DMX means X knows DM. So this is the given statement. I have converted this given statement into our setting. This is our setting that we will use. What is this setting? For some X, Sx satisfies DMX. What it means? It means for some X, student X satisfies DMX. Means some student knows DM. So how will we convert this into English first order logic formula? We will convert it like this: there exists X, Sx and DMX. Because I told you, with there exists quantifier we use conjunction. Okay, so this is how we translate this statement into this. Okay, student knows DM. What it means? Sx satisfies DMX for some X. So there exists X, Sx and DMX. What it means? It means there exists X such that X is a student and he or she knows discrete mathematics. This is the meaning. Let's see next example. All student knows discrete mathematics. All students know discrete mathematics. How can we translate it in first order logic? First, convert it in our setting. Our setting says that for all X, Sx satisfies DMX. This is our setting, right? Basically, this statement is saying for all student. Basically, this statement is saying that all students know discrete mathematics. So basically, this statement is saying that for all X, student satisfies. Basically, student knows discrete mathematics. Now we can translate it in first order logic formula. How can we translate? Very easily, like this: for all X, student X implies discrete mathematics, DMX. I told you, with for all quantifier we use implication. Anyone has any doubt in this? Okay, anyone has any doubt, then you can ask. So so whenever you have this kind of thing, whenever Px then Qx, then basically you write like this: for all, with for all you apply implication. Remember, with for all you apply, with for all comes implication. So whenever you have this kind of thing, for all X, whenever Px then Qx, you can translate it like this: for all x px implies qx. I told you with for all we apply implication. Okay, also with there exist we apply conjunction. There is some px where qx, basically there is some px which satisfies qx, then we will have there exist x, px and qx. So this is the takeaway point. This is the important point I am telling you, that for all usually paired with implication, there exist is paired with conjunction. This is the takeaway point. This is the important point. Okay, now what are other things that we can see? These things we have already seen. This thing we have already seen. This for when it is true, when it is false. This table we have already seen, if you remember. This thing, with this we have already seen. I told you when this is true, when this is true, when this is true, when this is true, when this is false. All these things we have seen. Now let's see negating quantifiers. Negating quantifiers. Let's see this. Negating quantifiers. How can we negate quantifier? So very easy. If you are negating a there exist quantifier, then what you will get? You will get for all quantifier. Then so basically what you do, see, negation of this, what will happen? Convert this there exist into for all, and this basically just insert this negation, you just propagate it. So when you apply this there this negation on there exist, you will get for all, and then you apply this negation to px. Similarly, negation of for all x px, what will happen? The negation of for all x px will be there exist x negation of px. So this is how you convert. So basically negation means, negation of there exist means for all negation. Okay, similarly negation of for all means there exist negation. So for example, let me give you this example. There exist for all y pxy. Let's assume that this is your negation of there exist for all y pxy. What will happen? Very simple. First, there exist will become for all x. This for all y will become there exist y, and inside you apply this negation of pxy. Okay, this is how you will get. So this is negation of quantifier. For example, let me give you another example. Negation of for all x there exist y, for all z there exist m, there exist n. So some psi. What will happen? Very easily. All you have to do is just propagate this negation. You propagate inside this negation. You propagate inside. So what will happen? When this negation is going inside, then what it will do? It will convert this for all into there exist. It will convert this there exist into for all. This for all into there exist. This there exist into for all, and this there exist into for all. And finally this negation will stop here. This you will get. Remember, this thing is same as this thing, because this thing is equivalent to this thing. So this is how you can negate a quantifier. Okay, this is the negation of quantifier. So this is how you can negate. For example, when you have okay, this table we have already seen. Now see the negation of quantifier table. This is how you can negate quantifier. Negation of for all will be there exist x. Okay, so Manisha is saying that now it's bouncing overhead. So let's stop here. And let's do one thing. See, okay, let's do one thing. Tomorrow we have class. In tomorrow's class, we will in the schedule. What is tomorrow's class? In tomorrow's class, we need to do, I think, the previous NET questions of mathematical logic. Previous year questions of NET. Okay, don't worry. Now we are not going to study anything. We have stopped. So okay, that is enough. Sorry. We have taken a lot of time. So that is enough. Now I am saying what we will cover tomorrow. Tomorrow, the previous year questions of NET exam we will cover. Okay, and when we will be covering all these questions, at that time we will see if anything is remaining, then that we will cover at that time. Okay, tomorrow we do not have discrete mathematics class. Okay, let's do whenever we have next class. Okay, tomorrow or the day after tomorrow, whenever the next class is will happen, we will solve previous year questions of mathematical logic. Previous year NET exam questions of mathematical logic we will cover, and all the concepts, all the questions, anything that we have left out in these two classes, we will cover those concepts, those questions at that time. So don't worry, if there is anything you did not get, then you can ask me. You can ask me individually, you can send direct message also, you can ask in the group also. However you want to ask, you can ask, but do not worry. If there is anything you did not understand, then I am going to cover it in the next class. Okay, so no one has to worry about anything. Of course we took a lot of time, maybe you have gotten tired, so let's do one thing. If at the end something was bouncing your head, then you can rewatch these last 30 or 40 minutes. The recording is available to you, and you can rewatch the last 40 minutes, last 50 minutes you can rewatch. Okay, and you can ask your doubts. Let me see if anyone has any doubt in the comment box. So many examples, you make things very easy to understand. Thank you Codebank, thanks for your feedback. And if you have any suggestion, if you have any feedback, then you can let us know. Any complaint, any feedback, anything, everything is welcome. We will discuss it, we will consider it. All your feedback we have already considered yesterday. Today you provided your feedback, you filled that Google form, and I and the Acadflix team, Abdul sir and everyone, we have already discussed about your feedback, and we are going to look into all the things that are troubling you. We are going to make it better and better. Mona, what is your doubt? I am not getting. So let's do one thing. You can ask your doubt on the WhatsApp. If anyone has any doubt that I did not cover, then you can ask in the on the WhatsApp. You can ask. You can direct message me, or you can ask on the group. Either someone else will help you, or I will answer it. Thank you, Manisha. So this is just a crash course. Also, I want to mention one thing. Just because this is a crash course, so we have to go very in a speed manner. You can see we have to go in a very speed manner. Only two classes for mathematical logic. But when we will study complete course, in this complete course, this mathematical logic we will study for around 6 or 7 classes. So you can see in these 2 classes I have covered almost everything. Just think how much I will cover in these 6-7 classes. So you can just think. So that's the benefit of complete course. In complete course we are going to cover every single thing in such a detailed manner. I will even write like this. I will even 2 plus 2 equal to 4. These kind of details we will go. Every single thing we will see in very detailed manner. Okay, so today's lecture is over. If anyone want to go, you can go. I am just looking at the comment box. Is it Acadflix crash course WhatsApp group? So we will make a group for discussion group. Acadflix discussion group we will make, and in that discussion group you can ask your doubts. Today we will create a discussion group. In that group anyone can ask. All the students of Acadflix can join that group, and in that group you can ask. Today we will create it. I think we have already created a Telegram group. We will also create a WhatsApp group so that anyone can ask anywhere. Yes, Mona, you can go. We are not teaching anything right now. Okay, thank you everyone. I am stopping this streaming because people are thinking that I am still teaching.